Hello everyone and welcome to Factorio. My name is Nasty. In today's video, we are going to be talking about some of the lessons learned from the green science video. The video was extremely long, about 2 hours long, going through every single design and doing a detailed breakdown of them. What I figured we would do today is I would go through at a high level some of the different concepts that we learned, mainly so that it's easier to refer back to this video, but also so that for those that didn't want to sit through the entirety of the 2 hours, I'm going to go through some of the concepts that we learned and try to hopefully help you in designing some of the more UPS optimized designs in the competition that I'm currently holding, but also just for posterity if you're interested in doing them yourself. So we're going to jump into the very first one right away. So the first problem that I want to talk through is desyncing assembly machines. So one of the core concepts that we use in a lot of the design videos that I've posted, along with also a lot of the designs that were featured in the red and green science UPS boards series, is using the concept of lead follower. Just as a quick overview to explain what lead follower is, all it effectively does is we read the contents of an assembly machine. It's important that we read both the contents and what we're including in crafting for the portion that we're going to talk about in a second. But for right now, effectively all this does is we monitor the conditions that are currently in the circuit network, and it tells us what is currently in the machine. This is a wonderful thing that we get for free in Space Age, because what this allows us to do is now we allow us to aggregate what the inserters are doing. So basically these inserters have a stack size of 16. We wind up saying just very simply with a decider combinator connected here to the assembly machine, hey, whenever it's over 16, let's go and output something. So we just send a very simple check mark, and we only send one value, because that one value means that that's the only time that the inserter ever has to make a check. So the inserter, in terms of the game engine, is actually considered completely inactive. And we can see that because I have the debug menu open. There's this little red icon that's over it. That means it's inactive only when it's needed. Same thing for the inputs. We can monitor the inputs here. The important thing to take into consideration is the automated insertion limit. We can't insert something if we're over that. Now, the automated insertion limit does not just count for the items that are currently in these two inventory slots. This also counts for what is currently being crafted. So we can see here that let's go down to 14. Technically, right now we're below the automated insertion limit, or we've actually reached it. Now we're allowed to insert it. We weren't allowed to do it before at 15. The reason is, if you look at the circuit network here, this is at 15, and 15 are the items that are being outputted to it. So why is that? Well, right now there is an item that is currently crafting. It's at 1%. The ingredients for logistics science, or green science, is one transport belt and one inserter. So currently the machine is using, in this progress bar right now, is using one transport belt and one inserter while having 14 items in a buffer for a total of 15 items. So that's what the automated insertion limit is. Doesn't matter for productivity in terms of the output, it just matters, this is the only thing that we care about, is just the input and when we're going to put something in. Okay, so that's the automated insertion limit. So you can set this value, when you're monitoring this, to any value. In this case, we've set it to exactly 15, so that's the exact automated insertion limit. Probably not recommended to do that, because that's kind of risky to do it, because it's basically saying that, hey, if any of the followers downstream are anywhere near or just like a little bit off of that automated insertion limit, like you can see here, this is at 11, 11, and 14, and 14. If it's over that, you're going to have an issue with desyncs. Now, that's not the root cause of the problem. So let's talk about what desyncs are now that you have kind of an understanding. A desync occurs when the assembly machine that's downstream is over the automated insertion limit, but the lead is under it. Or even worse, if one ingredient is over the automated insertion limit and the other one isn't. That will cause the machine to oscillate. I'll give an example in a second. So, first off, why do we even do this and bother with it? Well, the game engine, and we have an example here with no circuits, right? So you're going to start seeing these little yellow and green flashes that are happening. So what that basically means is that whenever an inserter is monitoring an input for what it needs to insert to, that's yellow. Anytime it's monitoring an output that it's going to grab, that's green. So yellow just basically means here, cool, every single time a recipe finishes a craft. So what do we mean by craft? So right now you can see that the inserter is actively putting things in because both of these were under the automated insertion limit. Cool. So now these are much higher because we can stack much higher than the automated insertion limit, given that the fact that stack inserters can stack up to 16 items, which is a nice thing. So they reduce the swing time. So right now you're seeing that this is subscribed to this entity. It's saying, hey, when can I go and actually put something in? Can I do it now? Well, I don't have to wait. I don't have to do anything yet because the machine hasn't finished a craft. The moment that it finishes a craft, all of a sudden that little red icon goes away. It's now actively considering, is there items on the belt? Is there items in the assembly machine? Do I need to put anything into the assembly machine? No, I don't. Great. And this is for 2 ticks. It monitors and makes this decision. So now it's going to go dormant and it's going to sleep until the next craft happens. Now it goes and checks again, both for the output and for the input. So what that means is that in a cycle of 8 items that it consumes, it creates 16 items because of the productivity bonus. So that means that there's 8 checks for this inserter and 8 checks for this inserter that are actively going to do something and be considered active by the game engine for 2 ticks. So that means that per cycle, these things are considered active for 16 ticks respectively, or 32 ticks if you don't, basically not at the same time technically. So 16 ticks, that these are going to be active. But that means that it's also doing that not just for these 2 inserters, it's doing for all of them. So if you have a very large stack like this here, that's not just going to be 2, right? That's going to be in a line here, that's going to be 12. So that's 12 inserters making a decision every 8 times for an inserter's craft. So that's a lot of decisions that are being made, or about effectively then I think it would be 12 times 8 decisions times 2 ticks, so that's 192 ticks that these things are going to be active for, when they really could only be active for literally the 2 ticks that they actually need. So you can think about this whole method here, this whole inserter clocking method, as an aggregation method. What it basically says to the game engine is make decisions with just these decider combinators and let the inserters make a decision only when they say yes. So that means that the game's decision making is boiled down to 2 components rather than 12. So the more items that you add to that decision, the better the reduction, because now it is, instead of it's a 12 to 2 ratio, it would be a 24 to 2 ratio, or etc., 24 to 1. So basically you just take all that and make it a aggregated decision by 1 component in the game engine. That's why clocking is so good. The problem is the desyncing issue. So let's talk about desyncing and how it happens. So how does the desync happen in the first place? So the desync normally happens if all of these are initially active because they're monitoring and trying to follow the lead here. So when this happens, normally you're going to have not full back pressure on your lines like this. So, or even, let's just even make it even more extreme. Let's go ahead and just make sure that we do have full back pressure the entire time, but there's a moving belt. So right now, this is going to create an arbitrary little gap in here, and it's going to grab and make a gap in there as well. The machine is going to start crafting, but by the time that effectively this machine is below the insertion limit and gets below 5 again, you're going to see that perfectly, and this just depends especially on spacing and consumption. Once this gets to the point where it can almost activate, we're going to go and get below that automated insertion limit, it activates and sends a check. It's going to go here and grab 4 inserters, 8, 12, and it can grab all 16, which is great. And then it can put those items in there. It's then going to grab the next item and put that in there as well. So this one was completely fine. So we see here this is 14, 14, and 2. This is 15, 15, and 16. So close enough. Not going to have an issue because they will effectively get very close to the automated insertion limit, and they should have the items once they start dumping the items out again. So you can see here that this is now, the problem is this is grabbed 2, and this one's grabbed all of it. So now it's a 15, 15, and 14. So this one's already 1 off just by this chance. That's not so bad. It's close. It'll eventually resynchronize because both of the items have been taken out and they're both the same quantity. So what happens to the next inserter? So the next inserter, by the time that this comes in and gets activated, you're seeing that it's active, but this inserter can't pick up anything yet because there's nothing in front of it. So it's missing the first full pickup cycle here. So because of that, it's going to grab 8 items and get stuck. And when this goes and happens, it's now waiting. And so by the time it can finally put in its belts, this one's already moved on to the next item. So now it's waiting and it cannot put anything in because both of this, the lead has already finished. The check mark is over. So now we've put 16 items in here, so we're off. So okay, not a big deal. It'll go and add it the second time we come around. Let's see what happens to the next inserter. So this one can pick up. 8 items, and now is waiting even longer because of the belt gap that's there. It can put those items in, and now it misses its cycle and only has 16 items in it. So now these are both flip-flopped. You can see that on the second cycle, this one's synchronized and was okay again. If you get to the last one here, if at any point in time one of these inserters goes and only picks up 8, for an example, in that checkmark instance, that's when the oscillation will happen indefinitely and will never fix itself. You can see here, this one grabs 16 items, and then it waits again, can go and activate, and it's completely fine. But now, they are kind of eventually going to synchronize, you would think, but they don't. So why is that happening? Well, because every single time it went through, basically this belt here, it grabbed one of the items, but missed a swing on the second one. So what's going on now is indefinitely, and this will never correct itself, the timing of what is currently inside here with this being blocked. Let's watch another one that's currently having this issue. This one's oscillating, again with 16 items. So the moment that it's crafting, the other one can always put in another item whenever this one's swinging. So this one's 21 and 5, this is 8 and 8. So because these are perfectly synchronized, they can both pick up by double swinging in 2 swings. So, but this one can never do that. So this one will never be able to catch up because by the time that it's ready to go and put in the next item here, this is still considered to be input blocked, even though this one's currently swinging. So it won't be considered blocked anymore the moment that we get under that value, but we only are going to get 1 swing. So these are always oscillating on a period, on, off, on, off, on, off, on, off, around the crafting cycle. So that happens if you start the circuit on a non-moving belt. So on a moving belt like this and you have perfectly placed gaps. So what can you do? So the easiest option is just to wait until you have back pressure. Let's go ahead and do that. So I have created a circuit here that is just going to go and say, hey, let's just wait until everything here is at a point where there is effectively just until we decide to turn everything on. So we wait until the moon symbol is gone, and then we can turn everything on. The moment we do that, cool. Every single assembly machine is immediately synchronized and has the exact same amount of items in it. That makes sense because all of them could pick up exactly the items that are in front of it. So this one has 14, 14, 14, 14, etc. 2 crafting output, 2 crafting output. And this will work indefinitely for forever, and we'll never have an issue. Even if you block the output, and you can see them here all just arbitrarily, like all stop. You're gonna see this one stops at 32, 32, 48 in this case, 32, 32, and 32. So they can have this basically stack up, but they're all over the insertion limit. They don't have an imbalance of inputs, so not a problem. And so you can keep on doing this, stopping, starting, stopping, starting. And this will never have an issue because they can constantly continue to put things in because they have a deterministic amount of items that are all synchronized with the lead. So what happens if all of a sudden we have, and this was a point of the competition, as I said, you could potentially lose supply at some point. Like let's say you run out of something like an input to like your smelting array and you start losing some, you have sporadic output. When that happens, you're gonna have basically now gaps in the belt. And the moment that there's gaps in the belt, there's a potential for you to desynchronize all over again like we had before. Let's make it even more exasperated by removing one of these items here. So the moment that that happens, you're going to see still here, everything is completely fine because they're always going to pick up exactly those items that are happening. But if it ever misses something where we were initializing the state, or especially let's say we stop this production, start it, stop it, start it, and we have, well, I'm not getting it to work here. Let's try it with the yellow belt to make it more extreme. Now you're seeing that this is undersupplied, which is fine. Like, it's because like in theory, what we would want is that this to pick up again the moment that we get supply again. Well, you're gonna see here that this doesn't happen, and we get into that same deadlock situation again, where you're gonna have desyncs all over again because it missed a swing. So if you ever have a bad supply line issue, or you have a bad like imbalance of one ingredient or the other ingredient, you can have this happen because they'll miss the items on the belt. And that's a problem with belt fed stuff. Also direct insertion too, if you ever are, for some reason, losing supply on an item. So because I gave that as a design criteria, I came up with some really interesting ways to solve the problem. So the first way to solve it was done, like initially was just back pressure, but it passed the output being blocked, but you had to always have back pressure. If the criteria is that you can lose back pressure, like I said, well, there's another more complicated way to deal with it, but I'll show how that works here next. Hey, Buck here. I noticed that 86% of the people watching my Factorio videos aren't subscribed to the channel. So if you are one of those wonderful people and you appreciate the depth of my research and find my videos helpful, I would appreciate if you consider joining the rankings of the legendary engineers that have hit that subscribe button. It really helps the channel grow and lets me keep making more content, so thank you. So the way to solve this problem completely is to do a much more complicated but useful startup sequence. So what you want to do is get the assembler in a state that it would normally never naturally get into, which is a state in which it has no items in here, but the output would be less than its typical output insertion limit being reached. So what is that output insertion limit? Well, you can calculate it. If you look at this, the automated insertion limit here is 15. So that means that the output would get blocked when these two items have been fully put in here. It finishes a craft, and then the item doesn't pull anything out. And then this would get to, without prod, would get also to 15, and then it would stop. In practice, that's not what happens. In practice, what happens is the inserters will be able to put the items in here once. Because of productivity, this will boost up to 8 items will become 16. And then when it completely drains those two 16 items, it'll finally get completely output blocked at 32. We can demonstrate that here. So if I go and I put all these items in here, let's go and just surround it with beacons and just make it arbitrarily here. Let's go and put 16 items in like we would normally have from inserters. We'll do the same thing, pause the time. Okay, and we'll unpause it. Watch the crafting cycle, stops here at 32. The moment that I grab an inserter to pull those items out, let's press 0 here, and we'll just grab infinity chest to put them into. Let's just rotate it, move forward a tick. It's gonna grab those items. You see that it's still output blocked, because it has to wait until all these items are drained before it can go and take those items out. And then, only then, are we allowed to pull the items out or start putting things in. And this is also the blocking condition. Okay, so that's the output problem. So the way that we want to do this is get it into a state where it will never be output blocked, because it will always be lower than the theoretical amount that's in here. So 15 is the value we want to. The really easy way to do that is to have it so that there are 8 science packs in here and nothing in here. That would never happen naturally. So the way to do that is to set effectively, we can do that with setting a stack size, or we can override the stack size ourselves. We wind up just saying we were going to want to put 4 items in. Why do we want to put 4 items in? 4 items are going to translate into 8 logistic science packs. So what that means then is we're going to always be below and never be output blocked when these get fully drained. So they can always craft, and they'll never be considered that it can't put some item into it. So how do we go and get the game engine to do that? So we do that with circuits in a clever way. So the way that this works is we still have that same lock that stops anything to go and put any item into the assembly machines until there's fully back pressure. And I have a little display panel to demonstrate that for us. So what we're going to do is we're going to turn on this priming sequence. Do that by pressing this check mark. I pause the game. So this moves forward, it's going to see a check mark, and it's going to start a clock for us. The clock is just going to count up arbitrarily. You're going to see that there's a filter that has been set here. This is much more complicated because it means that you have to understand the mechanics of the inserters themselves. You could do this maybe in a different way. I've done it with clocks because I know that it takes 4 ticks to pick up an item from the belt. So what we're going to do here is we're going to send that value. It's going to grab exactly 4 items, and then it's going to drop those into the assembly machine. And that's because the stack size was set to 4. So that means it's going to preload it with 4 items here. We can do the same thing here. We're going to send, the moment that we get to 30 ticks here, we're going to send again a pulse that is going to then grab 4 items from the inserter. Again, send the stack signal to B4, and it's going to put that now here into Logistics Science Pack. It's going to finish its craft, and now we're going to be exactly at 8. So that's the perfect sequence that we want. So just to showcase how easy this is once you have this set up, the way that this would work is you paste down the blueprint, wait until there's full back pressure. So let's go ahead and just make that happen a little bit faster here. Cool, back pressure has been achieved. You do this visually. And then what you do is you just press the check mark. It primes the 2 items. And then the moment that the clock is over a value that you want, that's kind of how I do it, then it says, hey, you're ready to enable. So then all you really have to do is you can either remove the lock signal, which would remove this condition, or what I like to do is I just like to basically delete everything so I can remove all these extra things. However, there's one extra thing that you have to do to take in consideration here. So setting filters is slightly less optimal than just sending a single value across the network and just turning it on and off. So nice optimization that was done that you can do here is you can take a second stage of a blueprint. So this would be the second stage. What it is it just has all the inserters already predefined here with just little check marks. They just have the conditions that we're not setting the stack size anymore, and we just have check marks. So now what we can do is you can still have this lock signal here. And then we can just basically go and copy this and paste this down. So the moment that we do that, nothing's going to kick off, but you can see that now all the settings have been applied to the inserters. So what we can do now is we can just basically delete this at our leisure. We can have them all the extra startup sequence to be done. And then when we're ready, you can either just turn this off, or even easier, just go ahead and delete it. Now what's going to happen is what you'll see is we have the benefit that we had above here, where we started everything from a full back pressure state. But the crafting is now at a very different value than you're even seeing here. So we have now 15, 15, and 8 items in here. So we have a total of 16 items and 8. What this now does is no matter what you do in terms of this running for an arbitrarily long time, the moment that we start losing back pressure here, let's go ahead and simulate that. What is going to happen is here, if we run this, at 64x speed, you're going to see that this is going to start oscillating. But you're noticing a very specific thing. These are now oscillating by holding 8 items. And this is now has 16 items in there, but there's 8 in here. What this guarantees is that the next time that you get back to having full back pressure again, the nice thing is what we're going to have, and you're going to see is, okay, they're still grabbing things kind of sporadically from the belt. But now this has naturally gotten back into a point where this fully synchronizes again, and we don't have the problem that we had above here. Because in the state where we were just around that automated insertion limit, and we're getting output blocked like this, the output block is now impossible. Because the stack inserters will always pick up 8 items and always be able to put 16 items in, so they always have to wait until 8. So by picking up 8, you drop under the limit of the output insertion limit, and it can always immediately be removing the output block from happening. So this applies to all kinds of designs, not only logistics science. So that same concept can be applied to anything. You can do this for engines. You can do this for any kind of machine that is going to have low insertion limits where you might have a desync and you could be output blocked. Is creating a good priming sequence that gets everything set up in the very first time, so that way you're going to be at a point where you're never going to be output blocked because it's impossible to do. Hopefully that's helpful to kind of explain some ways that you can get around the output limit insertion by kind of setting up a priming sequence to get the assembly machines into a state where they will always pick up items to just drop below the output limit. So if you want to go and use this method for your own designs, the way that I would approach it and recommend it to make it the easiest, so that you don't have to remember, okay, which check mark do I have to press, and especially if you're sharing with other people, this makes it a lot easier, is I create effectively multiple stages. So the easiest way to do this is just create a blueprint book. So I've just created one here called Green Science Multistage as a demo. So you create that as a folder, right? So this is going to contain them all. What you first do is you make sure that all your filters are set appropriately. You can set whatever the combinations are. In my case, I want to make sure here I've forgotten that I'm going to set the stack size. And so I'm going to go and apply that by pressing Shift here, apply it to all these inserters. And then here as well, I don't care about this one. Because in the end state, this one doesn't actually need to set the filters ever. It just needs to press the check mark and just make sure it has stack 16. This is going to be blocked because we know that, because it's going to have a lock signal on it, and that lock signal's here. Check mark will be activated in the second stage. Okay, cool. So let's go ahead and Control Shift, and we will press Control C, sorry, and then Shift to create a blueprint of this. We're going to call this stage 1. And I'm going to put this right here into this book. So then I'm going to go and create a copy of it. I'm going to move it over here, and I'm going to call this stage 2. And I'll make this a nice little indicator here. So now what I do is I trigger the condition that I would normally have, which is just pressing this check mark button. And to highlight this a little bit better, let's go ahead and just go ahead and put this back down. It doesn't really matter what state we're in. We just have to make sure that this check mark is done, and this gets us into this stage. Cool. So stage 2 is done. We go and copy this, save it. All right, and then finally, I'm going to go and create a copy of it, and I'm going to make a stage 3 for it. So stage 3 is going to effectively now be where we have the final end state. So we don't need this clock anymore, so we can delete that. And we also don't need any of these things activated, but to make it easy to paste down, we want to go ahead and turn both of these things off, just so that we can remember that. So now this is off. We're also not going to need this anymore. And we're going to have to turn off all these things and set these things back to having a stack size of 16. There's other ways that you can do this without setting the filters, for example. So I'll go ahead and turn all these on here. And one of the other things in this combinator I decided to do was set the filters. I'm deciding I don't need that anymore, so we'll go ahead and turn that off. The purpose is mainly just get everything now for these inserters exactly in the way that you want them to. And now what you can do is finally we can go to stage 3, highlight this whole thing, and we can save it as a blueprint. So why is this useful? So let's go and explain how this works now. Now with selecting the blueprint book, we can hold Shift and we can cycle through them, right? So if we hold Shift, place this down as stage 1, we now just wait until there's full back pressure. I like having little indicators like this. It makes it really obvious to a user what's going on. You wait until this happens. We wait until everything basically gets completely backed up. And we'll go ahead and just make it go a little bit faster because I'm impatient. And then we'll go to stage 2. We'll just press Shift and select it. And oops, I have screwed that up completely. So after that technical difficulty was dealt with, we're going to go ahead and go and grab stage 2 by holding Shift. And we're going to go ahead and just press Shift here and click. What that's going to do is apply all the settings that we had to this constant combinator, so we don't need to remember. And then we're going to get a nice little signal that says it's ready to enable. So now when we're completely done, we go to stage 3 here, and we go ahead and paste this down. And then we are good. One nice thing that I'd like to do is if I have a decider combinator like this, and I would basically just say, hey, if effectively the lock is equal to 0, cool, we are like whatever, let's say we have a little star signal, and this says delete build initialized, delete startup logic. This is something that I would probably do as a note. So now this is nice. Let's go ahead and just copy this for stage 3 here. And let's go ahead and delete the things again that we didn't want anymore. And we'll keep this. So now this is really nice for a user because again, they just go to stage 1, game speed 2, 4, let everything back up. Now we grab our blueprint book, go to stage 2, select it, everything is primed, get the ready to enable signal, go to stage 3, select it down, and we're running. So it's a little bit more setup work, but the actual implementation of getting it to work for blueprints is really simple if you just have multiple stages. Again, did we need all this? Technically you do for these inserters here, if you want to have the most optimal, which is just sending a check mark. You can still just set the filters by basically just applying, let's say, the outputs of transport belts and inserters in here, and setting both of those filters on the actual inserters here. That's another way to do it. It might be even better for when you have more ingredients in here. So, but this is a way to do it that makes it really simple so you can flexibly choose which strategy you want and then still use the most optimal, which is just check marks. Hopefully that's helpful as well. So that's it for this video. If you found this helpful, consider giving me a like and subscribing to my channel. It really helps out the channel a lot and helps make more content like this. One of my goals is to make shorter videos like this that helps practically break down some of the larger concepts that we have from some of my very long videos. and break them to be a little bit more tangible for me to remember it, but also for you as if you're creating a mega base, to be able to optimize some of your designs and understand some of the concepts of the circuits themselves broken down like this. I'm going to continue to create short forms like this as we go through the UPS Wars series. The UPS War videos are probably going to be very long, but this is going to be help to create more shorter breakdowns in case you are A, participating in the UPS War series and you want to improve your designs, or B, if you just want to get into mega basing and you want to design things like this, then this will also be helpful for other people in the future. So that's my goal for this channel in general, is to continue to help people build mega bases and optimize designs in Factorio. If you like that, consider again, like I said, giving me a like on the video and subscribing to the channel for more content like this. I really appreciate everyone already that has subscribed, and looking forward to what's to come next. So thank you for watching.